And welcome back to another LeetCode video. Today we're looking at LeetCode 1625, lexicographically smallest string after applying operations. This is a medium problem, and I'm going to show you how to solve it with a simple DFS approach. And of course, we're also going to do a runtime and space complexity analysis. That makes sense. All right, so let's get into the problem and let's see what it's all about. So we're given a string S of even length, and it consists of only digits from 0 to 9. And we're also given two integers a and b. In each step, we can apply one of two operations. We can add a to all odd indices of the string S. Digits post 9 or larger than 9 are cycled back to 0. For example, if the string is 3, 4, 5, 6 and a is 5, it becomes, now we're adding 5 to the odd digits, right? Becomes 3, 9, 5, 1. That means the last digit was a 6. We add 5, it becomes 11, but we're going to do a modulo 10, so it becomes right. And the second operation is that we can rotate the string S right to the right by b positions. For example, if the string is again 3, 4, 5, 6 and b is 1, that means we can rotate right by one position at a time, and then becomes 6, 3, 5. So digits at the end loop back to the front. Right, and we should return the lexicographically smallest string that we can obtain by applying the above operations any number of times on S. Just as a reminder, a string is lexicographically smaller than another string when they have, assuming they have the same length. If the first position where A and B differ, A has a letter that appears earlier in the alphabet than the corresponding letter in B. Now, for our digits from 0 to 9, 0 comes earlier than the letter 9, for example. Cool. Right, so here's some examples. We get some input string 5525. A is 9, meaning we can add a 9 to any of these digits if we wanted to, or we can do a shift by 2 positions. And it just iterates through a couple of examples here. And the fact that it shows me that as an example tells me already that, oh, I probably have to do the same thing in my code. Or that there isn't a simple way to do this, and that we rather need to actually perform these operations to explore the state space, to explore all possible numbers we can generate, and then pick the one that is the smallest. And that's exactly what we're going to do. So we're going to have a result, and because we don't know any better, we're just going to assume a result is our original string. And now in the course of our algorithm, of course, we're going to try to find a smaller string. Now, implement this in a recursive way, or you can implement this in an iterative way. I thought this time I'll just show you how to do it iteratively. Now, to do an iterative DFS, what do we need? Well, we need something to keep track of the stack, so what items are in the queue. And so we're going to use a stack, which is a linked list. It gives us O of 1, append, and remove one from end operations. And we're going to seed it with our initial string. That's where we start. And from S, we're going to explore all the possible numbers that we can generate from S. We'll add them to the stack, and so on and so on and so on. So we will, and that'll ensure that we generate all of the numbers that are possible. So we'll have a little while loop. And as long as we have a number in a stack, we're not done yet. Now, to avoid cycles when we generate these numbers, right, you can imagine that when we rotate enough times, we will end up with the original number. That means we want to terminate our DFS at that point. So what we will also need is, we need to keep track of the numbers that we've seen, or in graph terms, we need to keep track of the nodes that we've visited, where each node represents it. Right. So yeah, that's what we're going to do. And then the first step is we're going to pop the next number that we need to take from the stack. And we'll do a little check if S in visited. Oh, nothing to do. We're just going to ignore this number and continue. Otherwise, we need to add that number to our visited set, so that in the future, when we run to the number, we don't process it again. Right, now what we also need to do is we need to check, what is, well, S is now potentially a smaller number than our current result. So we also need to, well, take the minimum, right? So result is the minimum of result in S. And this will ensure that result gets assigned the lexicographically smaller number of result S. Right. Next, well, now what we need to do is we need to iterate over all of the children of the current number, of the current node. And we can generate the children using the two modification operations. And it's good enough if we just perform one shift or one operation where we modify the digits. And then we put that generated number back into the stack. So and then from that number, we will generate another shift or another iteration, etc., etc., etc. So it's actually quite straightforward. So what's the first number, the first child of the current number? Let's call it maybe t, right? Well, it's the string that we can shift, and we can shift by b position. So what we're going to take is we're going to take the string s from position b onwards, and we'll append string s up to that position. That represents a rotation by b positions. So now we've generated a new string, and what do? We just add it to the stack. Now we could also just say if t not in visited, then we do that. But we don't necessarily need it because we're already checking here, pull something out of the stack. Yeah. It's not wrong to keep it in there. Now the other operation is where we, increment all the odd digits by a. So that's the next t that we can generate. And I'll write this in a little bit more, well, as a one-liner. So what I'm going to do here is I'm going to iterate over all of the digits and indices in the current number s. So we'll have a little for loop for I, that's the index, and digit in enumerate s. So now we're iterating over them. And what we want is, well, we want to have digit in there. But if I is odd, we want to add a to it. So how do we do that? Well, we will wrap this digit into a string conversion, into a to int conversion, like so. So this doesn't change anything right now, but we need to have it as an int in order to perform some operations on it. So we will have it as an int, and now we need to add a. However, we only need to add a when I is odd, right? So let's multiply this with a factor a. Well, we either multiply it with 0 or with 1. Obviously, we only want to multiply it with 1 when I is odd, and otherwise with 0, so that digit doesn't get changed. So, and the way to do that is, I'm just going to write I %. You can just do I %. Because I %2 will be 1 when I is odd, and then we pick the 1. Otherwise, it's even, and we pick the 0. Almost done. We need to loop the digit around, so we have to take the whole expression where we modify digit module, and that should be it. And well, and now we just need to add that as well to our stack, and that should be the entire code. So let me just run through the test to see if I made a mistake or not. Add go. Right, and it passes. And now let's submit to make sure that it passes all of the tests, and we'll have a little look at the runtime and space complexity analysis. So this passes. That's good. Well, with our rotation, well, we have a string of length n, And well, how many times can we rotate a number? N times, right? And how many different versions of a number can we generate after rotation? It's also n. And because that is limited, and we are using a visited set, that means we're never going to actually process more numbers. So we're not going to run into more than n by n numbers in our stack. And that means we're going to have this as a time complexity, but also as a space complexity. And that's pretty much it. That's the whole thing.